weekend? Yeah, well, it's almost here. Okay, so chapter 6 today. Want to have everyone prepared. So if you could take a moment, if you haven't done so already, just check the PowerPoint lectures folder. All of the materials for today are in this February 16th folder, so you can just click on that. And so all 4 of these files we will be using as part of the lecture today. If you want to have those available, one is so chapter 6 PowerPoint, another is on correlations with an article there. The next one is the Excel spreadsheet that we're going to actually do some statistical applications. And then the last one is table 5 from your textbook. So the document I gave you is just back in the appendix of your textbook is where you can find it. So page 453. So have that in your hand. Okay, so let's begin. All right, so becoming acquainted with statistical concepts. So we're going to take about the next 6 weeks in class and just focus on teaching you how to do stats. So not everything, but enough that you'll be able to take this knowledge, and if you're doing a thesis, you should be able to do your own data analysis. So we'll go through several real data sets. So I've got a library of stuff from 20 years of experience that we'll go back through and just use for different analyses. So this is kind of an introductory chapter into that. So a lot of the concepts that we go through in this chapter will be common to you. You will have done this to a certain degree in the 216 class that I think everybody's required to take for this major. So statistics are a way of organizing and making sense of data. So there's a procedure that we go through. It's logical and methodical. So there's certain rules that we follow in the ways that we record and then organize and then make data so that we can interpret it and make sense of it. So it's objective. So the way that we place numbers into a spreadsheet and the analysis that we select is based on the question that we have. So your research question that you're familiar with, you should have an idea at least how you might want to approach that. And so you'll have some data in front of you at some point, and being able to put that data into a spreadsheet and then do an analysis to make sense of it in an objective way is really important to complete your project. So we want to describe the characteristics of the participants. So are your participants trained? Are they untrained? Male, female? What is their age, height, body mass? Sometimes in strength studies, it's relative strength more than absolute strength that we talk about that's important. So sometimes we want to test relationships between variables. So this is where your correlations will come in. So the Pearson correlation we'll talk about today. With the study that I asked you to download, we look at different positions, combine performance, and then playing success for the first 3 years. So they only go 3 years because anybody know what NFL stands for? Not for long. So it's 3 years is what they got. So they analyze their success over 3 years and correlate it with their performance at the combine. If we want to go beyond relationships, relationships are kind of the first step in establishing cause and effect. So we say that, well, there might be something there, and then we can actually see by conducting an experiment where we look at differences between groups or differences between conditions. So a treatment versus a control, and so on. And so over time, as an experiment is repeated, then we can begin to establish cause and effect. So the measures of central tendency are really important. So today we'll go over calculation of what the mean is, sometimes called the average, but also the variability around the mean. So you can have a sample that's drawn from a population. Is the mean of the sample going to be the same as the mean of the population? So you have this huge group of people, and because you don't want to measure everyone in this massive group, you randomly select a small group from that population and you measure the mean of the sample because it's a lot easier. So let me ask you that same question. Is the mean that you get for the sample going to be exactly the same as what you would have for the population? Not exactly. You'd hope it would be close. So the closer your sample is in size to the size of your population, the closer those means are going to be together. So today we'll discuss the concept of standard error. So what is the expected difference between a sample mean versus a population mean, and how that ties in? So the mean, you take the sum of scores and divide by the total number of scores that you have. So let's start from the beginning with relationships. So the association between variables. The Pearson R is probably the most common method of assessing association between variables. It's very easy to calculate using Excel, and we'll do some of this either today or next class. Sometimes called the interclass correlation. So anything inter means between, right? So between variables. So later on in the semester, we'll get to what's called the intra. Intra is within. So if for example, if you're giving a test multiple times to the same person, then you would want to calculate the intra because it's the same test to the same person multiple times. So inter means different tests. So different characteristics and how they might be associated. So in terms of correlations, you have a continuum anywhere from -1 to +1 with 0 in the middle. So the closer you are to 0, the less of an association that you have. On the positive side, you have variables that are proportionate to each other. So as one goes up, the other goes up. On the other side, you have more of an inverse relationship. So as one variable goes up, the other one would tend to go in the opposite direction. So we see both types of these correlations in health and human performance. As you think about different characteristics, different fitness variables, characteristics that would describe fitness. So we have health-related fitness characteristics. We have sport-specific fitness characteristics. For health, we have measures like cardiovascular fitness, which also is a sport fitness characteristic, but is also very important for health. So cardiovascular fitness, we have muscular strength, we have muscular endurance. Okay, so localized muscular endurance. We also have body composition and flexibility. So those are the 5 standard health-related fitness characteristics. And then we can go beyond that, and we have things that are also important for performance. We might also argue for good health, power, coordination, balance, reaction time, and so on. So it's sometimes useful to look at relationships between these fitness variables. So at the elite level, we have individuals that are the very top for a given characteristic, such as this Kenyan Eliud Kipchoge, is that the pronunciation? And so he's the current world record holder in the marathon. So last September Berlin Marathon, 2:01:09. He's also gone under 2 hours on one occasion, but that was under controlled conditions, and so they don't consider it an official world record. So on the other end of the continuum, you have guys like Bill Kazmaier. Okay, so one of the individuals that's the elite of strength performance. So you have endurance on this side, strength on this side. So his winning lifts were, or in other words, his PRs, 925.9 pounds for a squat, 661.4 pounds for a bench press, 837.8 pounds for a deadlift. What's really impressive is that the bench press and deadlift were done raw, so that means unequipped. So if you study powerlifting and stuff, you know that sometimes these athletes wear multiple these really tight suits that are very springy and elastic, very hard to get into. But he did those lifts without any equipment like that, so very, very impressive. So what would you expect at the elite level the correlation to be between these two, between endurance and strength? Probably not very high. Okay, so especially if you're looking at the elite level. What if you started to train Mr. Kazmaier like an endurance athlete? What would happen to his strength? Yeah. What if you started to train Eliud like Mr. Kazmaier? What would happen to his endurance? Yeah, right. So at the elite level, there's very little correlation between these expressions of physical performance. At the sub-elite level, you can have very good endurance and you can have very good strength, but it's very difficult when you reach the peak, the elite of the elite, to have a good level of both without it interfering with what you're trying to do. So I would say that Kipchoge probably does some strength training, but it's not for the purpose of being a strength athlete. It's for the purpose of injury prevention and improving his running performance. I would say that Kazmaier probably does some cardiovascular training, a limited amount, because it's good for your heart. Okay, so more of a longevity type of focus. So other correlations we see between physical characteristics. So this is just one from chapter 6 that pointed out. So looking at the correlation between long jump performance and standing height. Okay, so what this says is that the trend overall, each of these dots represents a person, and so at least, I'm not sure, it didn't say the sample this was from, but each of these dots represents a person from a sample, and so for this particular sample, it showed that as standing height goes up, standing long jump performance also goes up to a certain degree. So we would say that this correlation is around 0.6. So that represents a moderate association. So we can say strong associations are anything above 0.7 or anything below -0.7. So in other words, the closer you are to +1 or -1, the stronger the association, whether proportionate or inverse. So that made me think of this example. So Byron Jones, 2015 NFL Combine, height of 6 feet, weight 199 pounds, set the broad jump, standing broad jump world record at 12 feet 3 inches. And this is a still frame of that leap. And just amazing. So he's actually going to move his legs forward and then land, initiate that landing. So that's pretty amazing. But you can see that he not only has obviously the best standing broad jump in the world, but he also has a very good vertical leap. So you'd probably say there's a pretty good correlation between those two. If someone's a really good leaper vertically, they're probably also a pretty good leaper horizontally for the broad jump. So I was searching and searching, and I just couldn't find a study or anything where they'd actually taken a group of highly trained people and correlated those two. There's probably one out there, maybe you can find one, but I'm sure the correlation is pretty strong, probably at least 0.7 or above. So as one goes up, the other goes up. Okay, so I want you to go ahead and open the study from Kuzmits and Adams. And so you have some questions here, so you can just write these in your notes. And so this kind of gets to the heart of the matter. The whole reason for the combine, right, is to get a sense of future playing ability. And so the combine has been modified somewhat over the years. It's still being studied extensively to see if we can come up with a better or best battery of tests to predict future playing ability, because you're drafting people that do really well. So in these physical performance tests, the idea is, okay, well, if they can do really well here, there must be some type of association with how well they're going to play. So sometimes that's true, sometimes it's not. So in this particular study, there were 3 positions that were examined: running back, quarterback, and wide receiver. Okay, so it wasn't an exhaustive examination of all the positions in football. So, and then they followed them for 3 years after the combine to look at different factors that are important for each of those positions. So what I would like you to do, so you'll have to just look at 3 tables. And so you have the quarterbacks table, it's table 2. And so you can see across the top here the tests that were included in the combine at that time. And then down the column here, the first column, you can see different measures such as draft order, salary, games, quarterback rating. And then the same thing for wide receivers. Okay, so showing all those correlations. And then also for running backs with those correlations. So I want you to just take a few minutes, just look at those, just write them down somewhere in your notes based on these questions. So there's 2 questions for each position. I was just looking the other day at what the current combine tests are, and as of 2022, the Wonderlic was taken out. So that's no longer a part of the testing battery as of last year. So as you're listing these negative correlations and positive correlations, try to kind of work out in your mind what that means exactly. Faster time versus quarterback rating, and so on. Anybody need more time? Okay, a little bit. All right. Okay, so let's pull back together. So what'd you get for quarterback? So draft order and vertical jump. What'd you get for the correlation? Yeah, so that means if they were drafted earlier, what happened to their vertical jump? Went up, right? So moving in opposite direction. So if you're drafted sooner, that means you're jumping higher. So anything similar with broad jump? Yeah, so jumping further means drafted sooner. So those would be in, if you were to hypothesize that, that would be in an expected direction, right? So what about question number 2? So quarterbacks, what was the correlation between 40-yard dash and year 1 QB rating? Is that expected or unexpected? Okay, so that would mean to me that would be unexpected, which would mean a slower time in the 40 means what? A higher QB rating, right? So who's ever heard of Tom Brady? How well did he do at the combine in 1998? Not very well. Okay, so yeah, so that was unexpected, but it's not necessarily the most important thing, obviously, to be a great quarterback. It's also not, how strong of a correlation is 0.28? Not really. It's kind of a weak association, but it's kind of in the wrong direction that you would hypothesize. How about, okay, so again, Wonderlic test is out as of last year, but back then, for wide receivers, what was the correlation between the Wonderlic personnel test and year 2 salary? So that means as your Wonderlic score went down, what happened to your salary? It went up. Okay, so who knows on that? I put a question mark on that one. Okay, so maybe that's why it's out now. It's because it's completely irrelevant. Okay, so for wide receivers, what was the correlation between 40-yard dash and year 3 salary? Yeah, 0.28, which is also unexpected, meaning that as your 40-yard dash time went up, in other words, was slower, your year 3 salary also went up. So again, not necessarily in the expected direction for this crop of players. Okay, so number 5, for running backs, what was the correlation between 40-yard dash and year 1 yards per carry? That's kind of interesting. 40-yard dash and year 1 yards per carry, would you expect that one to be inverse or proportional? Okay, faster 40-yard dash should be what with yards per carry? Faster 40 means more, so that's opposite. So what was the correlation? Yeah, negative 0.34. So not super high correlation, but in the expected direction of faster 40 means more yards per carry in year one. So that was expected. For running backs, what was the correlation between 20-yard shuttle and year two salary? Yeah, so again, that would be expected. So a faster time in the 20-yard shuttle, faster time and higher year two salary. So there weren't really any correlations that were super strong. Most of them were below 0.5, which you get up to 0.5 and you're kind of in that moderate relationship zone. But some things there that were unexpected, which you look at a study like this, and this was 2008. This was kind of the first, I remember when it came out, this was the first study that kind of objectively looked at the NFL Combine. And there's been several studies out since. The last one I saw was about 2020. But they all kind of say the same thing, meaning that the NFL Combine is not a perfect predictive model for playing ability. So there's lots of other factors, maybe intangible factors, that are not as objective that teams will look at to determine future playing success. So it's just an exercise looking at literature and looking at correlations. Okay, so if we go beyond relationships and we look at differences between groups. So we have the t-test. So we have a couple of different types of t-tests. So the first is an independent t-test. An independent t-test, you're looking at two separate or independent groups or different conditions. So these groups or conditions are compared on measurement of one dependent variable. Okay, so let's take an example. Someone at this time is doing their senior thesis using an independent t-test. So they have a placebo group and they have an experimental group. And so they're taking one group of people, and everyone in that sample on two different occasions is either going to be doing the control or the experimental condition. So the control and the experimental condition, the order of those is being randomized. So everyone does 2 sessions. The experimental condition is taking a caffeine drink just before a step test. Okay, and then the control condition, they're serving a placebo in the form of a non-caloric but flavored exactly the same way as the caffeine drink. So participants are not going to be able to tell the difference. In other words, whether they're getting the placebo or the experimental. And then they're doing the step test, and then afterwards, the single dependent variable is going to be an assessment of blood pressure, okay, following the test. And I'll have to look through the proposal again to see the theory behind it and all of that. We know that, of course, caffeine increases heart rate, force of contraction, and so on. So you would think there'd be an increase in blood pressure, but we have to identify the time interval. So what time interval following the test is blood pressure going to be assessed? So that's the independent t-test. So it can be 2 different groups, or it can be one group with everyone doing both conditions. So either way. Okay, so if we go beyond just 2 and we have more than 2, so say 3, that's when we get into ANOVA. And so I think it's chapter 11 is when we start ANOVAs in this class. So single factor ANOVA means one independent variable. Okay, so there can be multiple conditions within that one independent variable. Okay, so I'll give you another example. So I love senior theses because it's on my mind right now. So we have another senior thesis going on this semester, looking at different footwear on squat force. So they have one independent variable, and they have 2 conditions under that independent, or 3 conditions under that independent variable. So different footwear. Okay, so barefoot squat, how many have seen that? It's kind of a trendy thing to do. Okay, barefoot squat. And then their other footwear condition is Vans. How many have? So one of my daughters loves to wear those with the checkered pattern, the Vans. Okay, so they want to see if that helps with squat. And then just regular sneakers, like cross trainers. So those are your three different conditions within a single independent variable, and then you're looking at those three conditions on one dependent variable. So they'll be doing a barbell back squat on our force plate downstairs, and so we're loading up the squat, and then they'll warm up, and then they'll do these repetitions where we'll assess different aspects of force, like impulse and all that. If you're in biomechanics, you understand what impulse means, but it's just one dependent variable. Okay, so then we're getting down to the dependent t-test. Okay, so this is also a very popular one. So Drew has got his senior thesis going on right now, and so he's looking at clapping push-up performance. How many have done clapping push-ups or seen them done? Hey, right? Okay, pretty hard to do. It's like doing jumping with your arms. Before and after whole body vibration. So it's a pre-post type of design. So you're looking at clapping push-up performance at one point in time before a treatment like whole body vibration, and then you're looking at the same dependent variable, which in this case is what we call the explosive power factor. That's the dependent variable. We look at it again at a second point in time. So that would be a dependent t-test, a pre-post design. Okay, so let me pause at this point. Do you have any questions, or maybe thinking about your own study? So Eric, yours would probably be right here, independent t-test. Anybody else? Corey, yours is probably more right here, pre-post. Trying to think, I forget what. A lot of you are correlation type studies, so you wouldn't even get into this. It would be more just the relationships. Tommy, yours is more a correlational type study. So it's all good. It's just whatever you want to study and then picking the right analysis for it. So do you have any questions about the differences here? Okay, all right, let's keep going. Okay, so why do we do all these tests? Because we want to generalize to the larger population. So you have this huge population, and it's really not practical, is it, to measure everybody in the population? So then you draw a sample. Sometimes it's a sample of convenience, right? So if you're at a college and you got to do a senior thesis, it's probably going to be your peers, and you're grateful, to have anybody that will participate. So you come and pick on the 105 class, and that's great because they have to participate in research projects. But the idea is to be able to generalize. So you take your results, and it's the generalization that is the benefit. So that's why we do research, is to improve practice or improve the way we live our lives. And so the generalization is the ultimate goal of research, where you have a take-home message. So what's the bottom line? What can I get out of this project? So I see, as I look over, all of you have projects that are useful, they're practical, that applied level 3 type of research that you can readily generalize and benefit how people behave and how people do things. So if the sample truly represents the larger group, then the findings can be inferred or generalized to the larger group, larger population. So key issues: how is the sample selected? Does it sufficiently represent the population? So will the sample mean be the same as the population mean? So no, it won't. We hope it'll be close, but we have ways that we can estimate the difference between the sample mean and population mean. So we'll go over some of those calculations today. So how good does the sample have to be? In many studies, random sampling is not done at all for practicality. And this discusses. It's a good section in your textbook chapter. Researchers are happy to have any participants that will volunteer. So, been there many times, and glad to have people that will willing to take time to be a part of a study. So sample of convenience, good enough for the purpose of the study. Oftentimes you'll see research where right at the very end, in the application section, it'll say the best possible generalization statement, which is the findings may be plausible in other participants, treatments, and situations depending on the similarity to the study sample characteristics. So you're looking at a study and say, okay, well, I can apply this as long as I'm a similar person to what was being studied. So that's why you go through the subjects section. So in your research proposal, describing the characteristics of subjects, because that has a lot to do with whether you can generalize or not. So common software used, Microsoft Excel. Another one that we actually do carry at this university, and it's free. You have to ask for it, but it is free for students and faculty, is SPSS, so Statistical Package for the Social Sciences. This is really nice to have. So especially when you're getting beyond just single factor ANOVA, going into multiple independent variables, multiple dependent variables, SPSS makes it really, really nice. So as you get down in your proposal to the statistical analysis section, you'll want to probably state that you're going to be using Excel. So as an example, a one-way analysis variance with repeated measure was used to evaluate differences in repetition performance between experimental protocols, muscle activation, the extension exercise, in case you're describing all of that. And then you put statistical analysis, in your case, you'll say will be performed with the software SPSS version, and then where SPS comes from. Okay, so how to write your subjects section. Really important. You want to give the reader as much information as possible on the background of your participants. So here's just another example. 15 recreationally trained men, 18 to 27 years old. All subjects had previous resistance training experience, 2.7 plus or minus 8 years. And then kind of describing what they were doing, typical diet, not permitted to use nutritional supplements, not on anabolic steroids or any other anabolic agents known to enhance performance. Then you talk about the physical activity readiness questionnaire, signed and informed consent in accordance with the Declaration of Helsinki. So anybody heard of the Declaration of Helsinki? It started in 1964, so it was a consortium for the ethical treatment of human subjects. So it's undergone revision since then, but it's sometimes common to place that at the end of your subjects paragraph. So you're in accordance with what most of the world uses for ethical treatment of human subjects. Okay, so central tendency. So we're using one number to describe a group of people. So there's three common measures of central tendency where we use one number to describe a group of people. And so they are the mean, the average value, so that's probably the most often utilized. The median, okay, which is literally the middle value. So you count up the values that you have, you add 1 and divide by 2, and you can get the middle value. So if your n, or the number of people, is an even number, the median will be a decimal. Then the mode, which is the most frequent value. Okay, all right, so other ways that we could describe a sample, not just with the mean, but also how much variability we have around the mean value. So do you have very little variability? Are most people scoring close to the mean? Or do you have a lot of variability where on average scores deviate a long ways on either side of the mean? So it's important to describe the sample in terms of the mean, but also how much variability there is. because that will determine whether you have a significant difference. If you have two different means and the standard deviations are relatively tight, that means close to the mean, it's more likely that you'll have significance versus two means with very large deviations. So if there's a large variability between two means, you're going to get a lot of overlap in scores. And so the more overlap you have in the variability between two scores, the less likely you are to get significance. So you'll see what that means here with some examples. Okay, so variance. So what does variance mean? What is the dictionary definition of variance? And then we'll go over an example. So it's the average of the squared deviations from the mean. Okay, so now we're going to get to an example on the next slide where you'll actually see and be able to process what that means. So the average of the squared deviations from the mean. Standard deviation is the square root of the variance. So you could say the square root of the average of squared deviations from the mean. And then the range takes into account the highest and lowest scores. So these are three ways of describing variability around the mean value. Okay, so here's an example, table 6.1 from your textbook. Okay, so we have a group of scores. So each of these represents a score. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you add up all those scores together, and you have this Greek symbol here that means sum. So you sum all those scores together and you get 45. So we want to know how much variability there is. We want to know the mean score, but also how much variability. So we have 45 and we have 9 scores, so we divide 45 by 9, and our mean value for these 9 people is 5. So the mean or the average value. We sum the scores and then divide by the number of scores to get our mean value. Okay, so how do we take the next step and get the variability? Okay, so we're going to go the long way first, and then I'll teach you how to use Excel where you can just go the short way. Okay, so it's important that you go the long way once so you can understand what it means in the process, and then once you've gone the long way, you understand the process, then you can use the short way. Okay, so what we want is the difference of each score from the mean. So you're taking the score and you're subtracting the mean. So in this case, the score is 6 and the mean is 5. So the difference between this score and the mean is 1. Is everybody with me so far on that? So all you're doing is just taking these, okay, so this score is 5, so what's the difference between that score and the mean? Yeah, there's not a difference, it's 0, it's exactly the same. Okay, so each of these scores, you're just doing that process. You're taking the score, subtracting the mean, and you're coming up with the difference. Okay, now if you were to add up that column, because mean indicates that there's some scores that are above and there's some scores that are below. So if you take all the differences and sum them up, what are you going to get? You're going to get 0. Right, so there's some negative numbers, some positive numbers, and so you add those up, you're going to get 0. So in order to make this meaningful, you have to take the square of each deviation from the mean. So we're taking the deviation from the mean, which is 1. Okay, 6 minus 5 is 1, and then we're squaring it. So 1 squared is 1, right? So then we go here, 0 squared is 0. Okay, so this score was 10, so 10 minus 5 is, the deviation is 5. 5 squared is 25, right? So we're just squaring each of those deviations. And then we add those up. So you have the sum is 45. This is your raw scores. You have the deviations above and below the mean, so that's 0. And then you have the sum of the squared deviations from the mean. The sum of the squared deviations from the mean. Does that make sense? Okay, all right, so let's go back. How did we define variance? The average of the squared deviations from the mean. The average of the squared deviations from the mean. So we've got all the squared deviations from the mean in this column. So I take the average, yeah. So how do I take an average? Add them up. What am I going to divide by? Yeah. Now, this is where it gets a little tricky because we want the variability to represent the population. Okay, so it doesn't do us any good for the variability to represent the sample. So what we do is we take n minus 1 rather than just n. So rather than dividing this number by 9, we divide it by 9 minus 1. So if you have a smaller number in the denominator, you're going to get a bigger number for your result. So if you don't believe me, divide 64 by 9, tell me what you come up with, and then divide 64 by 8 and tell me what you come up with. You get a bigger number because we would expect the population to have more or less variability than the sample. More, right? So we want a bigger number as our variance. So that's why we take n minus 1, is because we want a bigger number because we want the sample to represent the population. So we're going to take 64, and rather than dividing it by 9, we're going to divide it by 8 because we want that bigger number, okay? Now 64 divided by 8 gives us what? 8. So that's your variance. That's your variance. So that's the average of the square deviations from the mean. But that really doesn't make sense because, take a look, read this paragraph. Why do we then square, question number 2, why do we then square the variance to get the standard deviation? The answer is right here. Because the differences are squared, okay, so the differences are squared, the units of variance are not the same as the units of the data. So to get it back to the units of the data, we have to take the variance and square it. So therefore, the standard deviation is reported as the square root of the variance, and the units then correspond to those of the data set. So our variance is sum of the square deviations. It's not divided by 9, it's divided by 8 because we want a larger number. So we come up with 8, but then we have to take the square root of 8 to get it back down to the units of data. So then the square root of 8 then becomes 2.83. That's our standard deviation. So we would describe this sample as having a mean of 5 plus or minus 2.83. So that's where standard deviation comes from. So do you have any questions? How to do that or why we do that? Okay, all right. So how are we doing on time? I know it's a long day. So we'll go a little, let's go about maybe 20, 25 more minutes and then we'll wrap it up. Okay. So real data. So this is a study that I helped with a few years back. So comparing thigh muscle cross-sectional area and squat strength among national class Olympic weightlifters, powerlifters, and bodybuilders. Isn't that great? So we have people from each of the lifting disciplines that are at the elite level. National class. Olympic weightlifters, powerlifters, and bodybuilders. So these are people that have been training for decades at their given discipline. Are there similarities between how these different lifting disciplines train? Yeah, there's similarities. Do they all squat? Yeah. And so that was kind of our objective, is looking at squat strength, but then also cross-sectional area of the thigh. So that's done typically by right at the mid-thigh level. And so you take a skin fold and then you take a circumference, and we didn't have, because we were traveling to these different competitions where we could actually see people at this level, we didn't take an MRI machine with us. So we used an equation to estimate thigh cross-sectional area. So we had to get a skin fold, and then we had to get a circumference measure. Okay, so we found 5 national caliber athletes in each of these disciplines that allowed us to take those measures. So you can see this was a huge collaboration when I was in Illinois, and then University of Oklahoma, University of Northern Iowa. So lots of people involved trying to track down these national class people to see if they would let us do a couple measures. Okay, so we'll get into this part in just a moment, but what I'd like you to do now, I want you to go ahead and go out to Excel. And so this is the actual data. Okay, so there's a couple different tabs. I could scroll down here, make it smaller maybe. No. So here's the complete data set here. So we were able to find 5 national class bodybuilders, powerlifters, and so on. And so we took height. You can see both inches and centimeters, weight, pounds, body mass in kilograms, their age, body fat percentage, mid-thigh, skin fold in millimeters, and then their 1 rep max squat in kilograms. So for research, you use metric units there. So you can scroll down and you can see for powerlifters what their numbers were like. And then you can see for the Olympic lifters there what their numbers were like. So that's one spreadsheet. I'd like you to go back to the first one that was opened up, and I'd like to do some of that same process that you saw in the PowerPoint for mid-thigh circumference. So this is set up in that way, so you can see that process of getting the mean and then the variability. So these are all the things that I want to know. So the sums, the mean, the variance, the standard deviation, standard error of the mean. So how far, or what is the difference between this very small sample and the population? That's what standard error means. And then the confidence interval. So if you're measuring a very small sample, it's also important to report confidence interval, because that gives you an idea of the range within which you're likely to find the population mean. So because the sample mean is different from the population mean, if we can have this interval, that allows us to get an idea of the range within which the population mean is likely to be. So that's the purpose of a confidence interval. Okay, so do you have any questions before we get into this analysis? Okay, so like I said, we're going to go through the long way, and then I'll show you the short way. Okay, so let's start. For just bodybuilders on mid-thigh circumference, we'll go ahead and do the long way. Okay, so the first thing we need is to take the sum of these scores. So if you've ever worked with Excel before, what's the first thing you do if you want to put in a formula into a cell? Yeah, equals. Very good. So you'd want to just highlight this cell, so that's B9, and then you would just type in equals. Okay. So you can tell what's going into a cell up here in the formula bar. So whatever you're putting into that cell is going to appear up here in this formula bar. Okay. So what do we want to do? We want to sum. So just going to type in sum, and then you're going to open your parentheses. So just like this, sum, open your parentheses, and then we can highlight the range of cells that we want to take the sum. So to do that, you can either type the cells in manually or just highlight them. And then you're going to close your parentheses. So that's all there is to it. So it's equals, always start it with equals, sum, open your parentheses, highlight all the cells with numbers that you want to add up, close your parentheses, or alternatively you could just type B4 colon and B8. So everybody with me so far? Okay, so then to get your result, you're just going to click on enter there. So that's your sum is 302.81. Okay, so let's go ahead and calculate the mean. So to calculate the mean, you take the sum of scores divided by how many in this case? 5. Yeah, so now we're down here in B10. Okay, so the first thing you do is what? Equals, right? So we're just B10 equals. Okay, now you can highlight. You can either type it in. Highlighting it is easier. So all I'm doing is just highlighting that one. You can then go /, and then all you'd need to type in is 5, because you've got 5 scores. Just like that. So enter, and so there's your mean. So the mean mid-thigh circumference in centimeters. So these guys had tree trunk type legs here. The mean is 60.56 centimeters. Okay, so we've got a couple of the numbers we need here to start this process. So like I said, we're just going to do this once, and then we'll go to the fast way. So we've got the mean, now we want variability, right? So we want variance, we want standard deviation. So we've got to take the deviation of each score from the mean. Okay, so again, we're up here, C4. Okay, so if you put your cursor there, and what's the first thing we always do, right? Equals. Okay, all right, so I just need to click on that score, and then I want to subtract this score down here. Okay, so all I'm doing is taking the score, just like in the PowerPoint, this score, and then I'm going to subtract, and then I'm going to click on that mean right there. So there. Okay, now don't hit enter yet. Okay, so I'm going to show you a little trick. The way Excel works is it's going to move down a cell for each subsequent calculation. So to make this just a little bit easier, watch closely. What I want you to do is put your cursor right here, just in front of that B. So just in front of that B on B10. Okay, so what you're going to do is just put a little dollar sign right there. You'll see why we do this in just a moment. Then you're going to put the cursor after the B. You're going to put another dollar sign. So, just like that. So you should have this formula entered into this cell. Now, if you were just going to do that one deviation, you wouldn't need the dollar signs, but we're going to make this a little easier. rather than going through and painstakingly going through every single cell, I'll show you how, and a lot of you worked with Excel know how convenient it can be. Does everybody have this in cell C4? Okay, all right, so you're going to hit enter, and excuse me, so you have 5.24. I want you to put the cursor back on that cell, and then you see how the cursor is this wide white cross, okay? So what I'd like you to do is come down here, and if you put it right over that corner, can you see how it changes to kind of this little black plus sign right there? So that's what you want. So to make this easy, you can just hold that down once it's like that, and then just come down, and you've got all of your deviations right there. So that makes it a lot easier. Okay, so I'm gonna pause here. Do you have any questions? Okay, so again, this is the long way. We'll get to the short way in just a moment. Okay, so if I was to add this up, if I was to add this column up, what would I get, do you think? I get 0, because I have some deviations that are above the mean, some that are below the mean, so 0. So what I need to do is take the square of each of these deviations, and we'll take the average to get the variance. So to do that, first thing, you'd want to put your cursor in D4, and you would just start like we start everything else with the equals. Okay. And then you just click on the cell that you want to take the square of. And then I want you to look at your laptop. What symbol do you see just above the 6? Number 6. Yeah, so that's how you would do a square in Excel. So just put that in there, and then you put a 2. So that would let Excel know you're wanting to take the square. Just like that. So no dollar signs or anything this time. You just enter, and you've got your squared value there. So those of you who worked with Excel, you can use the decimal, the convenient decimal keys up here on the toolbar to go down to 2 significant digits. Why don't we go ahead and drag down so we have all of our squared deviations, and then we can use the decimal tool to go down to 2 significant digits. So we're here, so again, getting to where you have that small black plus sign right at the bottom right. So when it's there, you hold down the cursor, left cursor, and just drag down like that. So if you keep it highlighted, you can then just use your decimal buttons to add or reduce decimals. Oh, wrong direction. You can just come down and you just have 2 like that. Okay, so we need to put our lines back in, right? So I'm wondering, yeah, that's over here. So the lines disappeared on us. So you can highlight where you want those lines to be. And then you've got this little tool right up here that you can, right there, you can go ahead and put those lines back, just like that. Okay, now we need to take the sum of the deviations and some of the square deviations. So because we already summed the raw scores, we can just put our cursor right in the bottom right of this box. So if you put your cursor in B9 and just drag across, can just drag across, and you can see we were right. So you get 0 when you add up the deviations, and then you have a number here. So this is the sum of the square deviations. So 47.4 is the sum of the square deviations. So that doesn't do us much good. So what we want is the variance. And so we've already taken, there's our formula for variance, the sum of the square deviations, and we divide that by n minus 1. What does n minus 1 equal to? 4, yeah. So if you want, put your cursor right here in B11. You'll start it out just like you always do. You're just gonna go equals, and then you just highlight the sum of the square deviations. It's right there. And then you can just go /, and then probably just easiest to just type in 4, like that. And so you hit enter, and then you get 11.85. Okay, so we're gonna do one more, and then I'm gonna show you how Excel makes it super, super easy. So how do we define standard deviation then? It's not the average, it's the square root of the variance is exactly right. So all we have to do is take the square root of 11.85. So let's go ahead and do that. So just like always, it's equals. To do square root, it's SQRT. SQRT. So SQRT. So don't forget to type in the equals to start with. So equals SQRT. You're going to open your parentheses, and then you'll just click on 11.85, and then close your parentheses like that. And so that'll give you your standard deviation. Okay, all right, so told you we'd go through the long way once. Now let's do the super easy way. Okay, so off to the side there, I want you to put your cursor in C11. Okay, I'll show you how to do the variance and standard deviation. Super easy way. Now that you understand where the standard deviation and variance comes from. So like always, you just start with equals. So I want you to type in VAR. So you'll notice you have a few different choices here. You have the variance for a population, you have a variance for a sample, and so we want to make the inference for the population. So what we're going to do is you want to select this choice right there. So VAR.P. So all you really have to do is just double click on that choice. So as you begin typing, Excel will come up with some choices. So VAR.P is the population variance, and that's really what we want. So double click on it, and it's ready for you. So it's open the parentheses, all ready for you. And so all you need to do is just select your data range and close your parentheses. So VAR.P, because we don't want sample, we want population. Select your data, close your parentheses, and then you hit enter, and oh, that's surprising. Maybe it's the other way. Let me see. Why don't we go VAR.S? So maybe I'm thinking opposite here. So why don't we try VAR.S? Maybe it's the standard error that gets us to the population variance. So So same procedure. Let's go var.s. Same thing. So you'll highlight your data. And then you've got close parentheses. And it looks like that one worked for us. So the inference from the sample to the population is going to come in with the standard error. So I apologize, I got that mixed up. So standard error will tell you the difference between the sample variance and the population variance. Okay, so same thing with, let's take the same logic with standard deviation. So if you type in STDEV, and so you can see you have a couple choices there. So same thing as before. So thinking probably the .s to go with the sample. So you can double click the stdev.s, and then it's ready. So then you can scroll all the way down to enter your data. Close the parentheses like that, and then you've got consistency there. So the whole exercise to show you the long ways you understand how we get there, and then now that you know that, you can just use the short way from now on. Okay, so there's two more things that I want to do today. So you can see here the standard error of the mean. So that's, as I said, how much difference there is between the mean of the sample and the mean of the population. So the formula you can see here is your standard deviation, okay, so lowercase s divided by the square root of the number of people in your sample. So in this case, that's 5. Okay, so let's finish out these last two. That'll be the last thing we do for today. So standard error of the mean, because it's a sample. You want your cursor in B13. Okay. So start it with an equals. And so you're going to click on the standard deviation. So that's right here in B12. So equals B12 divided by, so forward slash, the square root SQRT parentheses 5. So B12 divided by the square root of n. So n is how many people you have in your sample. So the standard deviation divided by the square root of 5 gives you 1.54 centimeters. So that means you'd have 1.54 centimeters difference between the sample and the larger population. Okay, so confidence interval. That goes beyond the standard error, and now you're looking for a range. So what range of values are you likely to find the population mean? So very last thing for today, hang with me here. So to calculate that, we need table 5. So everybody, if you'd be willing, just take a look. This is table 5 from your textbook. And so you notice the very first column here is called the degrees of freedom column. So you remember from Stats 216 how you calculate degrees of freedom? So it's n minus 1. It's always n minus 1. So you're going to take the number of people in your sample, which is 5, and you subtract 1. So our degrees of freedom is going to be 4. So I want you to go down that first column till you get to the row that has the 4. Everybody see where that's at? Okay. Now I want you to go across the column, and almost always in statistics we use what's called a two-tailed test. So there are some cases, we're not there yet. I don't want to go into that today, but I'd like you to use two-tailed for today. Just take my word for it for today. Two-tailed test. And what is the probability value that we always use in HHP? What's the standard probability value? 0.05, okay? So I want you to go from 4, I want you to go all the way across the column until you get to the 0.05 column. So what number do you see there? Say it out loud. Yeah, 2.776. So why this is important, what we can say is that once we have our confidence interval, because we're at the 0.05 column, we're 95% certain that the population mean is going to be between two values that represent our confidence interval. So what if we wanted to be 99% sure? What value would we want to do then? Yeah, so 0.01, so you'd want to keep going. So you're at 4, so you're going to go all the way over to where you see 0.01, and so that's a lot higher value, right? But in this case, when we get our confidence interval, we can say we're 99% certain that our population mean is within this confidence interval. Okay, so let's continue, and then it'll start to come together. Okay, so confidence interval, we need to take the standard error of the mean, which we already calculated, and we need to multiply it by the confidence level from table 5. So let's just use 0.05, so I can live with 95% certainty that the population mean is going to be within these limits. Okay, so everybody, let's go to B14. And so, just like always, start with equals, and you're going to take your standard error. Okay, standard error is right there. And all you have to do is multiply it by the value from table 5. So let's go to 95%. So in Excel, to multiply something, you just use the asterisk symbol. And then what was the value again? 2.776. Okay, so that's good. This is how we're going to get our confidence interval. Standard error multiplied by the table 5 value. It's going to give us 95% certainty that our population mean is somewhere between that interval. Okay, so it's 4.27. Okay, so that's going to be a plus or a minus. So what does that mean exactly? So if I could have somebody write down the mean, 60.56. Okay, so somebody just remember that or write it down. I'm going to go ahead and go into whiteboard. Almost done for the day. Hang in here. Okay, so our mean was what? 60.56. Okay, so what was our confidence interval value? 4.27. So somebody add 4.27 to 60.56.
Adding it?
Mm-hmm.
64.83.
Okay, now somebody subtract 4.27 from 60.56.
56.29.
Okay, so our confidence interval represents these two values right here. So this is the mean of our sample, right? This tiny sample of 5 national level bodybuilders. But that's a pretty tiny sample. Okay, so if we want to say, what is the mean of the larger population, we can say that we are 95% certain, 95% certainty that the mean of the population is somewhere between 56.29 and 64.83. 0.83. So that's what a confidence interval is. Does that make sense? Okay, so if we wanted to be a little more strict, we could make a confidence interval for 99% certainty, but that would be a broader range, and that makes sense because if we want to say 99% certain, then we want to spread that out a little bit. Okay, so questions about today? Okay. All right, so I'm going to give you a little homework assignment. So what I want you to do, using the easy method, I want you to do exactly what we did for powerlifters. The easy method, the equals, the var.s, stdev.s, and Olympic weightlifters. Okay, so come back to class on Tuesday. All I want to see is that you have done exactly the same steps for powerlifters and Olympic lifters.
We don't need to send you anything, just bring it.
No, just want to make sure you have it there because we're going to continue working on the spreadsheet. Questions? Okay, have a great weekend.